Hello, Wroclaw. I'm really happy to be here again 4 years later at the biggest React Native conference in Europe. And what did you think of that previous talk? I thought it was amazing, and I have to tell you, and I'm speaking for the entire Hermes team, it really feels awesome when somebody else puts the effort in to study what you have done and to explain it. And to explain it much better than we could have explained it. I learned a few things about Hermes myself. So I think Radek really deserves another round of applause. I don't know where he is, but good job. All right, so my name is Tzvetan Mikov, and I helped create the Hermes JavaScript Engine at Meta. So I can tell that there are at least 2-3 users of Hermes in the audience. Can you make some noise so I can hear you? I need the support. Okay. For 2 people, you guys are really loud, I have to say. Anyway, last time I was here, I was really pleasantly surprised by the reaction to my talk. After my talk, a couple of people approached me to tell me that the talk was very technical, but okay. So let's hope we can live up to this standard once more. I want to start by telling you a little story. This is the sad fable of Joe Native and his slow code. Joe was sad because he was having performance problems in his React Native app. The startup was very fast because of Hermes, but there was occasional UI stutter when scrolling very long lists, when using complex animations, or when computing crypto hashes, or mining a bit of Bitcoin in pure JavaScript. Problems that we all have had, obviously. Joe, who was a very passionate programmer, very passionate, tried and tried during a 50-hour coding marathon. He swore, he drank gallons of coffee, he profiled, he optimized his code, he rewrote it over and over, but ultimately, he was faced with the fundamental limit of interpreter performance. He could not make his JavaScript any faster. It was beyond his control. Deadly tired, with a crushed spirit, but boiling anger, poor Joe was considering making his final move of total desperation, trying to rewrite some of his code in C++. But then, he wondered, what if I could leverage type information to generate efficient native code ahead of time? I would still be writing JavaScript, but I would be in control of performance, not the Hermes interpreter, which is actually great. And I could optimize as much as I need. Could I do that? Joe wondered. And the answer to that is yes. Yes, you can, Joe. You can do all of those things and more. As part of our cross-platform vision, we really want to unleash JS developers like Joe and give them access to the unchecked power that native code has to offer. Optionally, if Joe really wanted, he can even carefully perform unsafe operations, potentially not only creating harmless web JavaScript crashes, but also devastating native crashes, just as C++ developers regularly do. And look at him, he's so happy. He doesn't know what he's getting into. But seriously, he will mostly get tons of performance. And on that highly optimistic note, I am excited to introduce the next version of Hermes, which we have been working on for some time now, codenamed Static Hermes. Some of you may have already heard some speculation about it on Twitter. It was not meant to be a secret. It was on GitHub since day one. But we didn't really want to talk about it because there was nothing to show. Well, now finally there is something to show, and we are eager to share it with you. The main innovation of Static Hermes, as you have guessed already, is optional ahead of time compilation of JavaScript to native code. It brings us close to our goal of combining the predictability and high performance of C with JavaScript usability. And no, despite what the last slide said, natively compiled JS is completely safe by default, exactly as interpreted JS. So there will not be native crashes for Joe. To be clear, native compilation is not for your entire app, even though that is possible. You need to decide which parts of your code need to be optimized to the max, and only they get compiled to native ahead of time. The rest continues to use Hermes bytecode. And if you want to learn Hermes bytecode, I recommend a great talk by Radek, React Native EU 2023. You will find it on YouTube in a couple of weeks. Now, the really big change here is that in order to fully exploit native performance, Static Hermes relies on sound types. Now, even if you don't know what sound types are, remember these words, and we'll really delve into that a little bit deeper in a few slides. At this point, I want to make a big disclaimer. We are seeing encouraging results from Static Hermes, but it is still very much a work in progress. Right now, it is not suitable for anyone besides the most extreme hackers and enthusiasts, like Radek. It is still not easy to use. Many things are broken. If you tried it, which you can, because it is on GitHub, you might get disappointed. But rest assured, we are working on it, and it is getting better all the time. Some of the Hermes team is here with me in React Native EU, and they are submitting diffs as we speak. So it is improving at this very second. With all that said, we really wanted to share it early with the React Native community and to get your feedback. We also want to thank our partner in this, Amazon, for adding TypeScript support to Static Hermes, because internally we added Flow support. Amazon uses React Native in many of its apps, and it has been supporting us in growing React Native over the past few years. Okay, so this is a brief overview of the topics that we'll cover in this presentation. I could talk for hours about Static Hermes, but I will try to fit everything in the remaining 20 minutes or so. So first, we'll start with explaining why it is difficult to compile JavaScript to native. Then we'll explain what sound typing is, and we'll look into an example of actual native compilation so you can get a feel for it. Finally, we'll talk about something that became possible with Static Hermes, and that is zero-cost FFI. First, we'll look at an example which reads an SQLite database entirely in JavaScript without C++ or C. And then we'll dig into a little bit more detailed example of one simple native call, which is getenv. First, let's set the stage a little bit here. Why do we need Static Hermes? Isn't regular Hermes good enough? Well, as an interpreter, Hermes is pretty good. And we actually do have plans to make it about twice faster, which is a topic for a whole another talk. But ultimately, there is only so much performance that you can get from an interpreter. And that isn't always enough. One way for people to exceed that level of performance is to write extensions in C++, just as poor Joe was going to. That, however, can be quite difficult to write and to maintain. So instead, we want to take advantage of React Native developers' familiarity with typed JavaScript and compile typed JavaScript to native ahead of time. I know I'm repeating myself a little bit. You know this is about compilation to native. A valid question to ask here is, what makes compiling JS to native so difficult in the first place? Well, the answer is easy to see in the example like this one. We have a function, it takes two parameters, but we don't know their types. So all possible types, string, array, number, regular expression, whatever, and combinations between them need to be supported. The result is that if you wanted to compile this to native, you either would get a binary explosion of all type combinations, or you would just get interpreter-like performance, which defeats the purpose of native compilation. There are interesting solutions in the academia that I would like to acknowledge, specifically the excellent HOP-C compiler by Manuel Serrano. But unfortunately, it doesn't really meet our needs since it compiles every function twice and relies on heuristics, so performance is not guaranteed and predictable. We are not ruling it out, though, for the future. Okay, then. We already said that we want to use type annotations. Can they help? Unfortunately, not by themselves, because type annotations in TypeScript and Flow are unsound. There is that word again, sound, unsound. What does it mean? Unsound means that these type annotations cannot guarantee that the actual types at runtime are correct, that they are what we say here. How so, you might ask? Well, here is a very simple example. We have this function annotated with number. We call it with two array elements. Unfortunately, these array elements are out of range. So instead of calling the function with number and number, we're calling it with two values of undefined. So as you can see, we have broken the type checkers. As I'm sure you know, there are many similar ways to break the type checkers. And this is not a bug in TypeScript or Flow. It is just that given JavaScript semantics, this problem cannot be solved statically at compile time. It is a very difficult problem. Here is how Static Hermes addresses this problem in this specific example. On the left, we have regular Hermes executing this code. And as we can see, it's calling it with undefined plus undefined. On the right, we have static Hermes. Now, rather than call the function with undefined, it throws a range exception when we try to access elements that are not in range. So to recap, static Hermes modifies some JavaScript semantics in order to enable efficient sound typing at runtime. In other words, at runtime, the types of values are guaranteed to match the type annotations, which in turn allows us to compile that source very efficiently. The new semantics are opt-in on a granular level, and you can use them only where you need them. Plus, the new code and existing code can coexist in interop. And finally, as I mentioned, both TypeScript and Flow are supported. But wait, are we breaking JavaScript? We can't arbitrarily change how the language works, can we? Well, consider this. We are simply enforcing the behavior that the user declared they wanted when they wrote the type annotation. When they wrote that X is of type number, they certainly did not intend for X to occasionally be of type undefined. That wouldn't make sense. So technically, the program we had there was incorrect. We just caught the bug at runtime instead of silently ignoring it. So we are strengthening the TypeScript and Flow type systems by enforcing them at runtime. We don't necessarily view that as breaking JavaScript. But regardless of these philosophical arguments, it is all opt-in. So if you don't like it, you don't have to use it. But if you do use it, it will make your code both faster and more correct. So we would like you to use it. We have talked a lot about this in theory now, so it's time to finally look at concrete examples and understand what compilation to native means for performance and what it looks like. The example we have chosen is nbody.js. Some of you may be familiar with it. It is a part of a well-known computer language benchmarks game. It is a math-heavy benchmark with many property accesses. When we started compiling it to native initially, it was the same performance as Hermes, and that is 550 milliseconds. But now, as you can see, it is 10 times faster when compiled natively. So that is not pretty shabby. Plus, we're certain that there is more headroom. We can probably get to 20 times faster than Hermes. 20 times. Okay, so we have this very nice performance improvement, but what does the compiled code look like? Let's examine this loop from nbody.js. How did it become so fast? Well, this is how. Before Static Hermes, there were dozens of instructions executed for every line of this loop by the interpreter. With Static Hermes, it is much better. And by the way, I'm really happy to bring some low-level assembler to this JavaScript conference. In the next slide, let's put the native in React Native. Here we are. If you don't know ARM64 assembler, don't worry. I think you will still get the idea. The first thing to see is how few assembler instructions we have for the first 2 lines of the loop. We have 6 instructions. And most importantly, most of these instructions are very cheap. The entire calculation, the 2 multiplications and the 2 adds, are all performed in parallel by a single instruction, which is marked with red there, which is really impressive. And trust me, this is very fast, and it is quite exciting for compiler developers. This is the rest of the loop. Again, very few instructions. Again, you don't need to understand the details of this, but you can see how small the output is. And rest assured, this is indeed very fast. It is achieving performance close to C, much faster than Hermes, and we're not even done with it. It will become even faster. Sadly, I don't have time to explain how, but perhaps next year, when we hopefully would have shipped this. Now, a few more benchmarks. We can see the results of other benchmarks that we have created. They are in the Static Hermes repository. They are not as impressive, but it's still not bad. One of them is like 5 times faster. And we are still working on making them better. The next thing I want to talk about is zero-cost FFI, which I suspect might be even more exciting for some of you. But what happened here? This was supposed to be a very serious slide. I don't know. I shouldn't have used ChatGPT for this presentation. Let's keep moving. So early on, when we started implementing sound typing, we got an unexpected benefit. We realized that sound types unlock the possibility of very efficient native platform integration. We can call native platform functions with practically no cost, just as if we were a C program. This enables us, if we wanted, to implement platform integrations entirely in JavaScript without the need for resorting to C++ at all. So what problem are we really solving here? First, native extensions are complex and error-prone, and they require a non-trivial amount of code in order to implement and wrap a single call to a native platform API. Furthermore, those wrappers, which use JSI, can become expensive when they're invoked very frequently. We can give JavaScript developers another option. The zero-cost FFI in Hermes is literally that. Zero cost. It performs no conversions, no allocations, no indirections. It is exactly as cheap as performing a regular library call in C++. We have measured that the call overhead is between 15 and 80 times, not percent, 80 times lower than JSI when calling a native function. However, we have to be careful. As we all know, native functions can be unsafe and dangerous. we have made it very cheap to code them, but that doesn't mean that they should be coded irresponsibly. To ensure that, we have introduced a distinction between safe and unsafe code. This is very similar to another very popular system software language. I'll let you guess which one it is. Unsafe code sections trust that the developer knows what they're doing. Hopefully, Joe knows. We'll see. And they must be explicitly declared. Safe sections, on the other hand, disallow unsafe operations, so you cannot accidentally call a native function from there. So you have to be really deliberate when interacting with native code. You can do it, but you cannot do it accidentally. After all this talking, and to whet your appetite for zero-cost FFI, I wanted to give you a taste of what is possible. In this first example, we are accessing an SQLite database entirely from JS. First, as you can see, we need to declare some native APIs. These are the APIs exported by SQLite. Now, I did not write this by hand. It was generated by our tool, which takes a C header and generates JavaScript bindings that we can use. And this is the JavaScript source that opens the database, queries it, prints the result, and this is it. This is the entire source. There's no C++. This is it. This is what runs SQLite. And it actually does work. I was actually planning to do this in a live demo, but I got discouraged after I saw what Microsoft did yesterday. I couldn't compare with that, so here's a screenshot. You can see this is invoking Static Hermes to compile the demo on a macOS command line. There I'm just showing you the output. It is a true macOS binary, and we're running it. It is opening the database and printing the results. So, as you can see, you could even use Static Hermes if you wanted to write native applications for macOS or Linux or Windows, although we do not recommend it. But I find it amusing that it is possible. Okay, this second example will be a little bit more boring, but I hope it will allow you to understand a little bit more what is going on here. We have deliberately chosen a very simple native API for demonstration purposes. It is the cgetEnv function, which reads an environment variable by name. Think process.env in Node.js. Again, observe that this is all JavaScript. There is no C++, JSI, or anything like that here. And we're not going to spend a lot of time on this, but let's quickly go over what is happening. First, this is the external declaration that we're going to call. This is telling Static Hermes of the C function that we want to call. Here, we're converting the name of the variable that we want to take from a JavaScript string to a C string. Here we are calling the native function. Then we're converting the result to a JavaScript string. And we're freeing the temporary buffer that we needed. Very simple, very logical, although you should only do this in libraries. You should not do this in product code, obviously. And here, I would like us to examine a little bit closer how to declare the external variable, the external function call. And I promise you this is actually the end. There's not a lot more. First, we have a place where we can put options. Things like calling convention, platform-dependent things. It is an object, open-ended, where we can use it to add functionality. This is where we specify the name of the native function we're importing. We describe the types of its parameters. We describe the return type. And this is just a throwaway body that we need to populate in order to make the type checker happy. Since this is an external function, but it's still passing through to TypeScript and Flow, we just throw a dummy exception so that it doesn't complain that we're not returning a result. So yeah, this is it. For questions or suggestions, I'm highly encouraging you to use the discussions tab on the Hermes GitHub repo. The entire team is there. We'll be happy to hear from you. I have a link to Endbody.js that we looked at in the beginning, and there is a link to several FFI examples, including the ones we looked at. They do work. Feel free to try them. And we will publish the slides somewhere where they'll be conveniently available. Thank you.